Good day. We are Group 10 and this presentation is for Mecn2023 Fluid Dynamics. The focus of our experiment was to design and test a U-tube manometer integrated into a pipe to act as a pitot tube, with the goal of observing how airflow velocity affects the pressure difference. In essence, the experiment was aimed at visualizing the relationship between velocity and pressure in a flowing fluid, as described by Bernoulli's principle. The project was inspired by Michael Atkin's YouTube video, where he built a similar device to demonstrate how manometers and pitot tubes function. We adapted and expanded on his idea, constructing our own version to test it experimentally and record how well a simple manometer can be used to measure velocity-induced pressure differences.
To fully understand this experiment, it is essential to recall Bernoulli's equation, which forms the foundation of much of fluid dynamics. It states that in a steady, incompressible, and non-viscous flow, the sum of the pressure energy, kinetic energy, and potential energy per unit volume will remain constant along a streamline. Mathematically, this can be represented as the static pressure added to half of the fluid density multiplied by the square of the fluid velocity, then added to the fluid density multiplied by both the gravitational acceleration and the height, thus yielding a constant. This relationship implies that as a fluid's velocity increases, its static pressure decreases. The Pitot tube uses this principle to measure velocity by comparing two pressures: the stagnation pressure, obtained when the flow is brought to a rest, as well as the static pressure, which exists in undisturbed flow. The difference between these two values represents the dynamic pressure, which can be used to determine velocity using the equation V equals the square root of 2 times the dynamic pressure, all over the fluid density. Our setup was designed to demonstrate this fundamental concept, that changes in flow velocity can be directly linked to measurable pressure differences.
A smaller demonstration model was constructed to clearly illustrate the design and function of the experimental setup. This compact version consists of a horizontal pipe with a U-tube manometer connected, which is partially filled with red dye to allowing us to view pressure differences easily. One port of the manometer faces directly into incoming airflow to measure the stagnation pressure, while the other one is flush with the top of the tube to measure static pressure. As airflow flows through the pipe, an increase in velocity produces a corresponding increase in pressure difference between these 2 points, causing the fluid level on the stagnation side to fall and static size to rise. The full-scale setup that was constructed according to the same principle, using a larger pipe and a variable air source to enable more precise measurements. The system was carefully sealed to prevent leakage, and a flow tunnel was created, ensuring the manometer accurately reflected changes in pressure due to variations in air flow velocity. Overall, the arrangement effectively demonstrates the relationship between airspeed and pressure, according to Bernoulli's principle, where higher velocities result in lower static pressure and greater stagnation.
Once the apparatus was assembled, it was carefully inspected for leaks to ensure accurate pressure readings. The U-tube was filled with water to an equal height on either side of the tube before an airflow was introduced. The airflow was obtained using a hairdryer to simulate low flow speeds and a leaf blower to simulate high flow speeds. For each airflow setting, a height difference between the 2 columns of water in the manometer was observed. The readings were recorded to establish the relationship between the height difference and the change in pressure with increasing air velocity. The experiment was simulated multiple times at each speed to ensure the experiment's repeatability and minimize random error. The errors caused by environmental factors such as temperature and air turbulence were also considered during the experimental process.
The data collected from our experiment demonstrates a clear and consistent trend in line with Bernoulli's principle, the results of which are summarized in the table below. As shown, the height difference in the U-tube manometer increased with airflow velocity. At the lowest setting, the average fluid column height was approximately 53 millimeters, while at the medium speed it increased to just shy of 62 millimeters, and at the higher speed it reached an average of 87 millimeters. This progressive increase in fluid displacement indicates that the pressure difference between the stagnation and static ports grew larger as the airflow velocity increased. To ensure measurement accuracy, all readings were taken using a ruler graded in millimeters, with an uncertainty of 0.5 millimeters. This allowed for precise observation of the fluid height in the manometer. Additionally, a thermometer was used to record the temperature of the fluid, which was measured at 18 degrees Celsius. Temperature was recorded because fluid density varies slightly with temperature, potentially influencing pressure calculations. Visually, the fluid level on the static side rose while the stagnation side fell as velocity increased. Overall, the results confirm that our setup successfully behaved as a functional Pitot type system, with measurable differences directly correlating to changes in airspeed.
These results provide a clear validation of Bernoulli's principle in action. The increase in manometer height difference corresponds directly to an increase in dynamic pressure as the airflow velocity increased. Using the measured height difference, we can calculate the approximate pressure change and airflow velocity using the relationship V equals 2 delta P over rho. The steady increase from 53 mm to 87 mm across the velocity range strongly supports the theoretical prediction that as velocity rises, static pressure decreases while stagnation pressure increases. However, several sources of experimental errors were identified. An error while reading the manometer scale due to curvature of the liquid surface, minor fluctuations in airflow, and potential leaks at the pressure connection points could have led to monetary pressure instability influencing the readings. The accuracy of the ruler and temperature variation of the manometric fluid also contribute to uncertainty, as the density of the liquid affects the magnitude of the pressure difference. Despite these limitations, the trend observed remained consistent and reproducible across trials. This confirms the experimental validity and highlights the importance of calibration, consistent measurement techniques, and airtight apparatus assembly in achieving reliable pressure readings.
The experiment successfully demonstrated the relationship between airflow velocity and pressure difference in a controlled environment. The YouTube manometer functioned exactly as intended, acting as a reliable and visible indicator of dynamic pressure, much like a Pitot tube. The results were consistent with Bernoulli's theory, confirming that as flow velocity increased, so did the measured pressure difference, with the stagnation pressure exceeding the static pressure. The inclusion of a smaller demonstration model enhanced the understanding of how the setup operates and helped visualize the concept more effectively. If this experiment were to be developed further, we would consider integrating digital differential pressure sensors or using data acquisition systems to achieve higher precision and real-time monitoring. Overall, this assignment, inspired by Michael Atkinson's work, offered valuable insight into the practical side of fluid dynamics, bridging the gap between theoretical equations and real-world flow behavior. Thank you.